Hello and welcome. In this video tutorial, we're going to take a look at Distance Time Graphs Gizmo Lab. Now, although I'm going to be working this with you, I want you to try and pause the video and work the gizmo yourself so that you can independently gain confidence with how to use it and how to gain information from it, and how to create value from this particular assignment. By simply watching me do it, you may have a basic understanding of what to do, but you don't really gain as much as if you worked on it yourself. So again, remember to pause, rewind the video as you need to, but certainly pause the video to allow yourself to practice certain portions of this as you go. Then resume the video to see if you're doing it correctly. Let's begin. The first thing we need to do is we need to make sure that we are calling up the Gizmo activity. So we can find this located in Google Classroom, either the PDF or the Google Doc version. I currently have the PDF version opened up in a Cami editing tool to allow me to write on this PDF. The next thing we need to do is we need to click on the distance time gizmo graph. This link takes us to the Gizmo website. Now you'll notice I'm already signed in, but chances are when you click on that link, you may not be signed in. So the first thing you're going to want to do is click on the login button and sign in with your login information. If you don't do that, you're going to have a 5-minute timer that's going to run out and you won't have a chance to complete the assignment. So don't forget to sign in before you begin. We're going to be launching the Gizmo here, and we'll be going back and forth between the Gizmo operation on this page, on this tab, and the Gizmo questions on this tab. Occasionally, we're going to have to take a screenshot here and there. And when we do, we're going to be opening up a separate page to put those screenshots, okay? The Cami editing tool does not really allow me to add stuff in here, but what I can do is I can use the drawing features to sort of copy what the graph looks like, okay? Those of you using the Google Doc feature, you can use the copy and paste of the screenshot, and I'll show you what I mean when we actually get there. To begin this activity, it always starts with a prior knowledge section, okay, and a list of vocabulary. Well, the vocabulary we're going to be working with, of course, is speed, and we do need to familiarize ourselves and be able to use what's called the Y-Intercept. Now, the prior knowledge questions are not meant to be right or wrong. They're meant to be whatever you think they mean before we actually begin. So, Max ran 50 meters in 10 seconds. Molly ran 30 meters in 5 seconds. Take a second, pause the video, and take a few minutes to answer questions 1 and 2. Who ran farther, Max or Molly? Who ran faster? Explain. Okay, now to be able to answer these questions right here, sometimes they are just predictions, what you think, and the answers, of course, may vary. In this instance, there's a right or wrong answer, and I'll go over them with you. So who actually ran farther? Well, the one who ran farther is the one who ran the greater distance. Max clearly ran the greater distance. Who ran faster? Now, whoever ran faster is the one who completed the distance in the shortest amount of time. The shortest amount of time, of course, is the winner. So one way we can look at it is take 50 meters in 10 seconds, and if we divide those, we get 5 meters per second. And if we take 30 meters in 5 seconds and we divide those, we get 6 meters per second. That means Molly ran faster. Molly ran 6 meters each second per second, while Max ran only 5 meters each second. So clearly Molly ran faster. Now, during the Gizmo warm-up, this is where we learn how to use the actual animation and learn how to use the interactivity involved with the animation. Let's begin. The distance time graph Gizmo shows a graph of a runner on a track. You can control the motion of the runner by manipulating the graph, in other words, dragging the red dots. Let's take a look at that. So this right here, if I take this red dot, I can move it up, down, and notice it changes the runner's the starting position. Same way I can move this other red dot here and there, and it changes the runner's final position. Check that the number of points is 2 and that the runner under runner 1 and show graph and animation are turned on. Show animation turned on, number of points 2, everything is good there. The graph should look like the one that's shown, where 0, 0 is at the starting point and 440, that means 4 seconds and 40 meters, is the ending point. Click the green start button on the stopwatch. What happens? At this point, pause the video, click the button, and answer question number 1. As you can see, the runner runs from left to right for 4 seconds, stopping at the 40-meter line. Click the red reset button on the stopwatch. The vertical green probe on the graph allows you to see a snapshot of the runner at any point in time. Drag it back and forth. As you do, watch the runner and the stopwatch. Click the red reset button. The runner now goes to the beginning of where they are initially positioned. And if you move this green probe back and forth, you can see not only does the runner change the position, but the stopwatch also matches the time with that position. So if I moved it to exactly this position right here, which appears to be around 1.4 seconds, well, 1.4 seconds corresponds to about 14 meters on not only the picture, but the graph. What was the position of the runner at 1 second? The runner to 1 second, we can see the runner's toes are at 10 meters. What are the coordinates of this point? Well, the coordinates would be an XY coordinate pair or a time distance coordinate pair. So the time would be 1 second, comma, 10 meters. So 1 comma 10 would be the coordinate pair. When, that means what time, was the runner on the 30-meter line? Well, let's move the runner until he gets to the 30-meter line, toes are on 30, and you can see this corresponds to about 3 seconds. What are the points of the coordinate on this? Well, the time would be 3 seconds, comma, 30 meters. Activity A, runner position. We're going to click the red reset button on the stopwatch and be sure that the points, number of points is 2. In the Gizmo, run the race as many times with a variety of different graphs. The red points on the graph can be dragged vertically. Pay attention to what the graph tells you about the runner. If the distance time graph contains the point 4:15, what does that tell you about the runner? Well, let's actually move that in the Gizmo. That way we can answer the question in a very specific, complete sentence. So 4:15 means at 4 seconds, the runner will end up at 15 meters. I'm going to drag the ending one down here, and we're going to press start. And what you can see is the runner starts at 0 and ends at 15 meters in 4 seconds. The runner did not run as far, and the runner clearly ran slower. This tells you that after 4 seconds of running, the runner was 15 meters from the starting point. Number 2, look at the graph on the right. Notice where the green probe is. See, the green probe is approximately at about maybe 1.5 seconds. If you could see the runner and the stopwatch at this moment, what would you see? Well, at 1.5 seconds, the runner is approximately at 20 meters. So the runner would be about on the 20-meter line. But since it is a downward slope of the line, the runner would be facing left. Let's actually create this and see for ourselves. We're going to set this up at 22 and looks to be like 15. So about 22, 15, and if we click this to about 1.5 seconds where it was, there we go, 16. So at 1.5 seconds, you can see we're at about 20 meters here. And notice the toes are facing left. The person is facing left because the downward slope in here is a negative velocity. Number 3, look at the image below. From the Gizmo, what must be true about the runner's graph? Well, you can see that the runner is, well, it's got a big stride, so the runner's running pretty fast. We can see the runner is at about 25 meters. And you can see that on the stopwatch, it says 3.25 seconds. So the graph must include the coordinate point 3.25, which is the time, and 25 meters. The graph has a positive slope. We know this because the runner is facing right, and right is considered a positive direction. Number 4, the point on the graph that lies on the y-axis, the vertical axis, is called the y-intercept. What does the y-intercept tell you about the runner? The y-intercept indicates the starting position of the runner. It's where the runner is at time equals 0. Now for part 5, we're going to set the number of points to 3, and then we're going to create a graph where the runner starts at the 20-meter line, runs to 40, and finishes at 30. So number of points to 3. We're going to start at 20, run to 40, end at 30. Start at 20, run to 40, end at 30. Looking like this. Let's create this graph. We can use the Cami editing tool to put this in here. So we're going to draw a line from actually undo that. Better if we put a shape in there. So I'm going to put in a line from 20 to 40. There we go, just like that. Then I'm going to put another line from 40 down to 30. Just like that. And that's the same graph that was created right here. What is the y-intercept of the graph? Well, the y-intercept is 0 seconds and 20 meters. Activity B, runner direction and speed. Run the gizmo several times with different types of graphs. Remember, the red points on the graph can be dragged vertically. Pay attention to the speed and direction of the runner. Number 1, create a graph of the runner that is running forward from left to right on the gizmo. Sketch the graph to the right. Well, that's pretty easy. We could use the one where we start at 0 and end at 40. That clearly is a runner going from left to right. If the runner is moving left to right, how will the graph always look? The graph will have a positive slope. In other words, it will slope up from left to right. Okay, now what will it look like? Well, if we draw a graph in here, I mean, one possibility would simply be a graph that looks like this. Any graph that you produce, no matter where it starts from, as long as the slope is upward, that would be correct. This is just one possible example. Number 2, click the red reset button. Create a graph of a runner that is running from right to left. Sketch the graph. Well, we could do exactly the opposite. Start at 40 and at 0. You can see the runner is running from right to left. So what must be needed in order for a runner to go to the left? The graph will have a negative slope. So as long as the slope is positive, the runner will go from left to right. As long as the slope is negative, the runner will go from right to left. So according to the one I created in the Gizmo, this is just one possible example. Number 3, change the points to 5. Create a graph of a runner that runs left to right for 1 second, rests for 2 seconds, and then continues running in the same direction. Sketch the graph. Well, number of points to 5. Now, if I'm running from left to right, I need to start at a lower position and get to a higher position, right? To have upward slopes, in other words. Well, to go from left to right, we need to go from left to right for 1 second. Then we need to rest for 2 seconds. So from 1 to 3 seconds, we can have a flat slope or no change in position. And then we can continue moving forward. So it might look like this. Run, stop, run, all in the same direction. How does a graph show a runner at rest? The line will be horizontal when the runner is at rest. In general, how does a distance time graph show which direction the runner is moving? The runner's direction is given by the slope of the graph. A positive slope means the runner is moving in the positive direction. Right. A negative slope means the runner is moving in the negative direction, which would be from right to left. Okay, going back to create that one example of a graph here. Go ahead and draw the line. So I drew a graph that kind of looked like this. We went forward for 1 second. We stopped for 2 seconds. And then we went forward for another second. Number 5, with the number of points set to 3, create the graph shown to the right. Well, here's what we're going to do. We're going to start at 0, 0. We're going to go to 2 seconds, 10, and then 4 seconds, 40. So set the number of points to 3, 0, 2 seconds, 10, and 4 seconds, 40. Reset. This is the graph on the image right here. Where does the runner start? The runner starting at 0. Runner starts on the 0 meter line. Where will the runner be after 2 seconds? Well, the runner will be at 10 meters. Where will the runner be after 4 seconds? Let's see, we're all the way over here to 40 meters. In which time interval do you think the runner will be running most quickly? Pause the video and try and figure this one out yourself. I'll give you a hint. It corresponds to the slope of these line segments. The interval in which the runner is going to be running most quickly should correspond to the interval with the steepest slope. You saw that from 10 to 40 meters, the runner ran a lot faster. Consequently, there's a much steeper slope here. So from 2 to 4 seconds, the runner will be going more quickly. Again, steeper slope, faster speed. Number 6, click the start button, watch the animation. What about the runner changed after 2 seconds of running? Well, after 2 seconds of running, we run faster. So the speed of the runner increased after 2 seconds. Part 7. Speed is a measure of how fast something is going. To calculate speed, divide distance and time. In the Gizmo, the units of speed are meters per second. In the first 2 seconds, how far did the runner go? Well, 2 seconds, runner went 10 meters. In this time interval, how far did the runner go each second? Well, 10 divided by 2 means each second the runner went 5 meters each second. Therefore, what was the runner's speed? 5 meters per second. Per second means each second. Now look at the last 2 seconds on the graph. In the last 2 seconds, how far did the runner go? Well, the runner went from 10 meters to 40 meters. So the runner went a total of 30 meters. In this time interval, how far did the runner get each second? Well, the runner went, if we follow the concept of slope, the runner went 30 meters in 2 seconds. So 30 meters in 2 seconds averages to 15 meters each second. So what was the runner's speed during the second time interval? 15 meters per second. Click the red reset button. Experiment with a variety of graphs focusing on the speed of the runner. In general, how can you estimate the speed of the runner by looking at the graph? So I'm just going to put this down to 2 points. So if we start with a graph like this, you can see the runner is going very slowly to 10 meters. Notice the steeper the line, the faster the runner. Activity C. Now, for activity C, to do number 1 here and to copy all these images here, what I'm going to do is I'm going to open up another Google Drive, a Google Doc that will allow me to copy and paste those images into the assignment. And what I will do is I will turn in this separate Google Doc file along with the assignment when I'm ready to do so. Open up the blank one. Title it. And I can call this Activity C part 1. And I'm going to number them off. 1, 2, 3, 4, and 5. And what I'm going to do is I'm going to copy and paste the descriptions next to each one of these. So my first one, I want a picture of where runner 1 wins the race. And the second one, I want a picture where runner 2 wins the race. The third one, I want a screenshot of where runner 2 catches up and passes runner 1. Then I want a screenshot where runner 2 is going in the opposite direction. And then lastly, I want where each runner is going a different speed, but both reach the finish line together. Okay. The first one is where runner 1 wins the race. Now, in order for runner 1 to win the race, runner 1 needs to have gone farther in the same amount of time. The time interval would be 4 seconds. So let's create something like that. Well, what I'm going to have is I'm going to have a runner 1 is going to be in red, and runner 2, we're going to click on runner 2. I'm going to show the animation, but I'm not going to show the graph, okay? Well, actually, yeah. Runner 2, I could start runner 2 at a different point. Like I could start runner 2, let's say here at 10, and let's say runner 2 only gets to that point right there. Well, resetting this, you can see runner 2 has a head start. Runner 1, way back. But when we go, runner 1 passes runner 2 and ends up at the finish line first. This could be an example of something where runner 1 wins the race. Oops. Let's go back and try that again. Right click, copy, and paste it in. Okay, there's the first one. Number 2, what might it look like if runner 2 wins the race? Well, runner 2 wins the race. It's kind of the exact opposite, right? So runner 2 wins the race. Could have something like this. Say we have runner 1 and actually going back to number 1, let me kind of point this out. Actually, this here, although this is runner 1 winning the race, actually this is better suited for number 3, where runner 2 catches up and passes runner 1. So actually, I'm going to hold off on that one. Let's go back to this first one again. Okay, and I could create something like this, where runner 1 gets to the 40-meter mark and 2 seconds, and runner 2, they start at the same point, like this, and they end up at the finish line at different points in time. So you can see they're both getting to the same finish line, but runner one got there way faster. So this, I guess, would be a little more appropriate for runner one winning the race. Copy that one there. Runner two winning the race. Well, kind of the exact opposite, right? So I'm going to put runner two finishing the 40-meter mark sooner, and runner one just kind of running at any old pace. And if I reset this, you'll clearly see runner two gets there in about 2 seconds, and it takes runner one a lot longer to get there. This would be an example of runner two winning the race. Number three, runner two catches up and passes runner one. Okay, this is the one I was mentioning earlier, in which case we'll put this down to 2 points. And I'll start with runner two here. Runner one is going to have a head start. So runner two catches up and passes runner one. Runner one has the head start, red has the head start, and gets only to a certain point, right? Red has the head start. Blue catches runner one and passes and ends up winning the race, right? This would be an example. Why? Because runner two has the steeper slope, therefore runner two is going faster. Runner two is going in the opposite direction as runner one. Well, I could just have runner two start at 40, end at 0, and have runner one start at 0 and end at 40. You can see they're clearly going in opposite directions. Okay, and lastly, another possibility would be each runner goes at a different speed, but both reach the finish line together. Well, in order for that to happen, they kind of have to have different starting points. So I'm going to start runner two it to, let's say, 20. And they both end up at the 40-meter line, but they kind of get there in different speeds. So you can see they're running at different speeds, but they end up at the crossing the finish line together. Okay, this is how we complete activity C, part 1. Now, these are just suggestions. There are countless other possibilities that you can encounter as well. Number 2, based on your experiment, answer the following questions. How does the graph show if a runner gets a head start? The runner with a head start will have a higher Y-intercept. Letter B. How do we know which graph shows which runner is faster? The faster runner has the steeper slope. Part C, how does the graph show which runner wins the race? The graph that reaches the 40-meter line first is the winner. How does the graph show a runner going back and forth? The line on the graph would have positive and negative slopes. In other words, the graph will go up and down. What does it mean when two runners cross? The point on the graph where two runners cross is where they have the same position. In other words, same location. They're just pointing in opposite directions. For part 3, for runner 2, turn off show graph. Click the new to generate the random graph so that you can't see runner 2. Then click start and watch her run. Then try and adjust the graph for runner 1 to see. And so basically, we're going to turn off the show graph. We're going to start it again. And so now we have a random new graph. And if I run the graph, I can see what this person is doing. It's very, very slow. So if I move this, I can see the person is starting, runner 2 is starting somewhere around maybe 8. Okay, so what I can do is I can move runner 2 to kind of reflect that. So maybe I start runner 2 at 8. Looks like their toes are together. That's good. Then notice as according to this slope right here, runner 1 would be going too fast. So I got to make that slope a little bit more flat. And you can see at 4 seconds, she ends up at about 17, 18 meters, maybe. Somewhere around there. Right, and there we go. You can see they're running side by side. So that's just an example of what you can do to challenge yourself to figure out how the graphs match. In the last section, use the gizmo to model and solve the following word problems. Write the solutions in the spaces below. Sketch the graphs you have made to solve the questions to the right. Well, here we have a dog chasing a cat towards a tree. The cat has a 10-meter lead and runs at a speed of 6 meters per second. The dog runs at a speed of 8 meters per second. The tree is 30 meters away from the dog's starting position. Which animal will reach the tree first? Well, you can see the dog is going to be, let's see, the dog is, so which one's running 6 meters per second? Well, the one that's running 8 meters per second would be the dog. The cat has the head start, you can tell here. The dog is starting at 0. Notice where they end up, okay? Notice where they end up. So the 10-meter lead, we're going to start the cat at 10 meters. We're going to give the cat a slope of 6 meters per second. So we're going to go up to 16 over 1 second. And that means the cat would end up at about 30-something meters right here. The dog has the 10-meter disadvantage, so it's 10 meters behind, and has a slope of 8 meters per second. Thus, the dog would end up at this position over here. Okay, who's going to get to the tree first? Well, the tree's 30 meters away. If you look 30 meters right here, that corresponds to the cat's graph getting to the 30-meter mark before the dog does. Cat reaches the tree first in about, it looks to be about 3 1/3 seconds. Part B, a police officer is chasing a purse snatcher down a street. The thief runs 9 meters ahead of the officer and can run 20 meters in 4 seconds. That's 5 meters per second. The police officer can run 32 meters in 4 seconds. That's 8 meters per second. How long will it take the officer to catch the thief? All right, so the thief is 9 meters ahead. So what we're going to do is we're going to start the thief. I'm going to make the blue line. I won't use blue. I'll just use different colors. So the police officer is going to start at 0, okay, and has a slope of 8 meters per second. So I'm going to make a graph that looks like that for the police officer. We're going 8 meters in 1 second. But the thief has a 9-meter head start. So I'm going to start the thief right here at 9, and the thief is going to only go up 5 meters for every second. So that means we're going up to about 14. Something like that. And if you look at where the positions intersect, there we go. If we look at where the positions intersect, there we are. We can see that the police officer is going to catch the crook because this needs to, I wrote this a little bit too high. This needs to be down. Whoops. Down. Come on. Well, just delete that. Start over. Okay, shape. So we need to be down here at around 9 seconds and going at about 5 meters per second gets us up to 14 in 1 second. And you can see right here, according to the graph, the police officer would catch the thief at what looks to be about 3 seconds. In a football game, one team receives from the other team. At the moment the ball receiver catches the ball, he's at the 40-meter. He's 40 meters from the nearest tackler. The receiver runs left to right. That means we need a downward slope at 10 meters per second. So let's draw that 40 meters. 10 meters per second. Oops, sorry, I have the wrong one there. It's the receiver is running 10 meters per second. So the receiver is running forward 10 meters per second. There. The tackler is running from right to left, meaning in the negative direction, at 6 meters per second. So that's the one where we're starting 40 meters ahead, and we have a slope that goes down 6 over 1. That would put us about right here. How long does it take before they collide? Well, we've got to estimate that. It's about 2-point-something seconds. I'm going to estimate about 2.5 seconds. How far did the receiver go? Well, the receiver goes about, looks to be about 25 meters before they actually collide. Part D, the tortoise challenges the hare to a 4-hour race. The hare is so confident of winning the race that he allows the tortoise a 10-kilometer lead. So we're going to make sure that these are kilometers, not meters. The hare runs at a speed of 14 kilometers per hour, but stops for a 2-hour nap in the middle of the race. The tortoise plods along at 4 kilometers per hour the whole race. Who gets farther in 4 hours? Okay, so I'm going to change this up. We're going to start. The tortoise is going to be running from 0 to about 14 kilometers per hour, which is about right here. I'm going to take a 2-hour nap. It's about right here. Okay, oops, change the color on that. Sorry about that. We're going to make the tortoise the black line here. So the tortoise runs 14 meters, rests for 2 hours. Then all of a sudden the hare gets a 10-meter head start and goes at a pace of about 4 kilometers per hour, which would be about this. It's kind of up 4 over 1. And the tortoise ends up, now the hare is going to run at the same speed on the other side. So it's going to be 14 kilometers per hour. So I have to go from 14 up to about 28, roughly. About 28, yeah. The tortoise is about 26. Hare, about 28 kilometers, goes farther than the tortoise. Part 5. How are distance time graphs useful? Explain, and if possible, discuss your answer with teachers and classmates. Well, basically, distance time graphs show starting positions, direction of motion, and the speed of the object through the slope. If there are 2 objects, the graph will show which object is moving faster, which object has a head start, and when, and where for that matter, the 2 objects cross paths. This concludes the tutorial for the distance time metric Gizmo lab. I hope you found it helpful